So we'll get started now. This is the first couple chapters, chapter 2 and chapter 3 are really difficult for most students because there's really more chemistry and biochemistry than there is more, anatomy and physiology. So that's only the first two chapters. After we get through the first two chapters, chapter 4, we talk about tissues, which we'll talk about next week when we go through a little bit about our histology and what microscope slides look like. So we'll do a little bit of that at the end of next week. So make sure you start looking at the lab sheets if you already have your Marieb and Mitchell lab manual, and you're looking for the chapter on tissues. In the back of the chapter, then you'll see a review 6A. That's optional if you want to use that review to kind of learn. They have questions. They have you attempt to draw what certain, what certain microscopic slides, what certain tissue samples look like. So then it reinforces what we're discussing. And again, what we're trying to do is start from the ground up. All of our body are made out of hundreds, right, of different type of cells, and they're going to work together to form some kind of organ system. And then all these organ systems made out of all these different cells interact with each other. So then we have a person with conscious thought, with ability to change and modify behavior about who we are, right? It's kind of crazy, but we're all these trillions of individual cells that are interconnected, that turns us and allows us to be who we are. And all it takes is a few cells to get infected, to mutate, and then we have serious issues. So, chemical basis of life. What in the world is this? So this is a 3D rendering of what a protein should look like. So when you look at this, these are proteins structurally, and what you'll see in a protein is that number one, they're made out of amino acids. We have 20 types of different amino acids, and different proteins have different arrangements of the 20. And we'll talk about that at the end of chapter 2, actually at the end of this chapter as well. So all of these, what looks like ribbons right here, are different arrangement of the amino acids. And when you have different arrangement of amino acids, it's like what happens when you have a real long line of people. It doesn't just stay straight, it usually curves a little bit. So what we're going to see is when we have a long line of amino acids, there's going to be some curvature, some kind of other structure that we're going to see that's going to be imparted on it. The amino acids, they're made out of, lots of different elements and atoms, and they start interacting with each other, and they start to form different type of shapes. All right, those shapes we call structures. So when you see all these ribbons and all these are different amino acid chains that are going to be in ribbon or alpha helical form. Some of you might have heard of a beta helix, which is a DNA. This is an alpha helix, single strand only, whereas a beta, whereas the double helical structure has 2 strands. So these are all strands of amino acids bound to each other, interacting with each other, because these are all atoms and they're gonna start to interact. And then they have this shape. And then you'll have shapes between all these different other areas of the strand. They start to interact, and then they start forming the actual structure component of it, giving the protein its actual ability to work. Now, let me go through this. And again, with basic chemistry, we're not going to talk about moles, so don't freak out. We're not going to talk about things like the ideal gas law. So we're going to talk really basic about this chemistry structure, okay? Nobody likes moles. Nobody likes, going through that. Even chemists really don't like it. So when we look at basic chemistry, what do I want you to know? Number one, what is matter? What is mass? What is weight? So matter, anything that occupies space and has mass. Mass is the amount of material or matter in that object. Now, what I want you to know is the difference between mass and weight. Weight has the gravitational force acting on any given object of a given mass. Weight changes, in other words, depending on where we are. The weight of your body, all the trillions of cells in the body, all the water, all of the right little metals that we have, the weight is going to be about, if you're me, about 200 some, right, pounds on the surface of Earth. But what happens when I'm in space? There's no gravitational pull. So even though my mass hasn't changed, I don't all of a sudden just, if I'm in space, I just took a spacecraft there. Well, what happens? I didn't all of a sudden lose a lot of cells. So the mass doesn't change, but my weight does. Why? Because weight is dependent on gravity. And in space, there's no gravity. All right, so just know the difference. Now, elements and atoms. Elements is like your periodic table of elements, right? Simplest type of matter with unique chemical properties, composed of atoms of only one kind. So elements are made out of atoms. Atoms are the smallest particle of elements that has chemical characteristics of that element. So atoms are your protons, electrons, neutrons. That's an atom. The atoms of the element will interact with atoms of other elements. So then they will start forming little type of bonds. And we'll talk about that coming up. All right, so take a look at this picture. We always know, and this is one of the cool things about physics and about, right, when we start talking about thermodynamics and all the different activity of atomic structure. The weird thing is this, and it is cool and weird at the same time. We always know where the nucleus is of any atom. It's always in the middle. The nucleus is a combination of proton, positive charge, and neutrons. Neutrons have no charge, but they have mass. So it gives that nucleus this positive charge, full of mass, a little bit heavier sink right in the middle. That's going to be very important. Now, the number of protons and the number of electrons are always the same of a given element. So if I have an element that's got the periodic, the actual number, atomic number of 7, that tells us we have 7 protons. We also should have 7 electrons. All atoms are going to be uncharged. The only time where they might have charge is when you interact 2 different atoms. So when we talk about an atom, the number of protons and the number of electrons should offset. The number of neutrons can differ. So we'll talk about that in a second, right? There are some atoms that have 1 or 2 more neutrons. So it's an isotope of the original atom. So neutrons for us aren't going to be a big deal, but we will talk about special times when we use some kind of isotope so that we can have a good look at if you're, an example of using radioactive isotope is for clinical use when we're trying to see if you have a thyroid disorder. So I give you a radioisotope for iodine. That iodine will get picked up by your thyroid. The more active the thyroid, the more iodine it picks up, the more it glows. And the more it glows, when I put a kind of like an x-ray machine on there, the more I can pinpoint which area of the thyroid is more active than it should be. But that's about the only time in our class we'll talk about additional neutrons and isotopes. We'll talk about this, electrons the most. Electrons are weird. There's a reason why we call electricity electricity. Electricity, yeah, you're probably wondering why I'm using those terms now, right? Electricity is caused by the movement of electrons. So when we have movement of electrons always allows us to have some kind of current going through. And as a current goes through with an electron, you're going to have energy. Electrons are energy. And that is a big thing that we'll discuss right here. Our body doesn't have any copper wiring, right? We know that. But we do have something very similar. We will use some kind of modified bioorganic kind of wiring to move electrons around when we start talking about how we make ATP or energy. So electrons are energy, and in our normal day life, we see electrons going through copper wiring, gives us electricity, gives us energy. Well, in our body, we see electrons moving through our cells, moving through components of our mitochondria. And as electrons go through those components, it also gives us energy. So no matter what we're talking about, when we mention electron, right away, I want you to think somehow or another, it has to pertain to energy, or forming it immediately, or breaking it apart. So it's something to do with energy. So atomic number, we also talk about it. It's probably easier if I show you the periodic table. So most of you guys have seen this before. Here's the periodic table of elements. And what we're going to see is there's a couple things I want you to know. Number one, when you're looking at this chart, obviously the 1, the 2, the 3, the 4 up here, those are going to be the atomic number. The atomic number is going to be the number of protons. So if I say this, look at number 12, atomic number 12. You look at 12 and it's magnesium. With magnesium, now we know with 12, it has 12 protons. And I just mentioned, if it's got 12 protons, it's got 12 electrons. So 12 protons, 12 electrons. So what happens next? You look on top right here. And in our columns, you'll see numbers. 1, 2, 3, 4, 5, 6, 7, and 8. Now, the weird thing is this. If I look at magnesium, I have 12 protons, 12 electrons. Perfect, right? Well, what we're going to see is not all of those electrons will be available for this atom to react and form bonds. In other words, I don't have 12 different electrons that can form bonds with 12 different other electrons if I'm going to put 2 atoms of magnesium together. Now, I'm not going to go into much detail, but the electrons, the 12 electrons in magnesium, lies in shells, right? There's a 1s1, the 2s2, 2p, right? Those shells means that some electrons are closer towards the nucleus. And because it's so close towards the nucleus, those electrons are going to be kind of, right, is going to not be available because it's attracted too much by the protons in the nucleus. And that atom is going to, and what we're going to see is the first 10 electrons of magnesium, the first 10 are not going to be available for any binding. It's going to be attracted to the protons closer to the nucleus. It's not going to be available for binding. You look up here, this tells you the number of external electrons readily available for binding. So out of those 12 electrons, 2 electrons will be on its external shell. That external shell then allows us to have these 2 electrons available to bind and react to other atoms. Now, so we take a look right here. Magnesium, 12 total electrons. If you look up here, 2 valence electrons readily available for bonding. Sodium, 11 electrons, 11 protons, only 1 available. Now keep in mind, right? When you see something like sodium and potassium, how many times have you seen something like, let me see if I can add something here. How many times, and I'll remove this in a second. Have you seen sodium, not as sodium like this, but sodium with a positive charge, like this, right? The only time we see sodium with a positive charge like that is if that sodium has been reacted with something else. If we take sodium and allow it to mix with, let's say, chlorine, right? What happens then? Then you have a positive charge. Why? Well, here's what happens. With sodium, sodium right here has 1 extra electron on its external surface. right? It's got 11 electron total, but 1 available for binding. So it's got 1 extra electron. Now, what sodium can do is go through all this chart, right? It can try to bind and gain an electron. Now it's got 2 electrons. And then get another one, get to 3. And then remember, we look at only this number on the outside, right? So for 13, right? So it's 1 valence electron, 2, and then you go all the way to 13. 3 valence electrons, 4, 5, 6, 7, and then 8. How do we know it's 8? It's right here. Now, the 8th one right here, the 8th one is special. This column are our, right, noble gases. This is the most stable configuration of all the electrons. So all of these atoms and elements that are in this row. So let's take the row number 2 with lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, and neon. This row right here, all right, all of the elements that are to the left in green, in yellow, in orange, all of them to the left of the neon, well, they want to have neon stable configuration. They want to have 8 total electrons on its valence shell. It has then, at that point, fulfilled its octet rule. And at that point, it is at its maximal stability. Now, should be a general review of chemistry. So just keep that in mind, right? It should be a general review of chemistry. If it really makes no sense, read the book and kind of go over it. Hopefully they go into a little bit of detail about this. Again, right, this should be general chemistry material. General doesn't mean easy. It just means that it's not that specific, right? Here, these noble gases. Well, helium only has 2 electrons, not 8. Well, what happens is after helium has its 2 electrons, it has filled the 1s2 shell, and it's at its most stable configuration. So hydrogen, with its 1 electron, wants to gain an extra electron somehow to become helium-like. Carbon has 4 valence electrons. What happens with carbon is, how many times have you guys watch a movie, watch a TV show, and they talk about how we're looking for extraterrestrials sometimes, right? We're talking about space. We're looking for carbon-based life forms. Why do we use that term carbon-based life forms? Simple. Carbon is smack dab in the middle. Carbon will not be able to steal electrons or take electrons because it's smack dab in the middle. And what we're going to see is for carbon to work, it has to share electrons with anything it binds to. And if you take a look, carbon can form, right? It's at 4, it has to gain 1, 2, 3, 4 electrons to become neon gas-like. In other words, it can bind to 4 different other atoms. If it can bind for 4 other different atoms, guess what? Right? This carbon can bind to a lot of very stable other atoms. If you have a carbon, bind with another carbon, with another carbon, with another carbon, that's a lot of bonds. And now we can start forming a large structure like DNA, like proteins, all because of the stability of carbon and its ability to bind with 4 other constituents and form very, very stable bonds. Now, we'll talk about bonds in just a second, but it is one of those things where we do expect you to have a little bit of knowledge of chemistry, right, before we start this class. So if you don't, you're gonna have to catch up a little bit. Right now, I'm not gonna, again, this is the very basic levels that we kind of, hopefully you guys in high school, in your Gen Chem classes in college have taken. Again, this class transfers to UWM, transfers for grade at UW-Madison. So there's a little bit more stringent nature of it because it is a 200 level college transfer class. Let's go back here. Right, again, atomic number number of protons, which also should equal the number of electrons. Take a look at it. Carbon had 6 total protons, 6 total electrons, but 2 of the electrons are really close to the nucleus and cannot take part in any binding. That leaves 4 more on its outer shell, able to then bind and react with other atoms. Oxygen, 8 protons, 8 electrons. Now, remember, it's not the total electrons we're looking at for its ability to bind. It's the number of electrons on its outer external shell. The electrons that are closest to the nucleus, they're going to be attracted by the positive charge of the proton. So it won't be able to react with anything else. For oxygen, when you ever heard of oxygen? Well, usually in oxygen, right? But also in water, H2O. So H2O means you have 2 hydrogens for every oxygen. Why? Well, because oxygen only has 2 electrons on its outer shell. So let's take a look at here. Oxygen, 8 total electrons. You take a look right here, all right? And now we're gonna see it's got 6 on its outer shell. It can react with 2 other atoms. All right, now isotopes, mass number and isotopes are very much related. If you change the number of protons, so if I get to 6 protons and I add another proton to it, I change the atom completely into a different element. Here's what I mean. If I have 6 protons and I add another proton, it turns it into nitrogen, right? So if you change the number of protons, you change the nature of that atom. If you change the number of neutrons, you still keep the number of protons. So if I add a neutron to, let's say, iodine, right? Right here, iodine has 53 protons, 53 electrons. If I add another neutron to it, did I add to the number of protons? No, right? I didn't add to the number of electrons either. I just add to the weight. By giving it a little bit more number of neutrons, I add slightly more mass to it. By adding mass to it, right? I add more neutrons, I add more mass without adding any more charge, without adding more protons. By adding more mass, what are we going to do? Turn it into an isotope of iodine. Now here, with hydrogen, right? What have we done? Number of protons the same between hydrogen and deuterium. What I've done with hydrogen is add a neutron to it. By adding a neutron to something, I have made an isotope of that original element. I haven't changed it by adding a proton. All I've done is put a little bit more weight to it. Deuterium is usually added with water to form what they call heavy water. Heavy water is used in a lot of chemical reactions and a lot of nuclear reactions, right? When we have a nuclear power plant. Now, obviously, you don't see many deuterium in our body, right? So the only time we do see isotopes used is when we are using isotopes as a way to treat somebody for an illness, or use it as a way to identify, right? If you have, like we mentioned, if you have hyperthyroidism. Now let me see how many people are here, and I'll tell you, usually most of my class is going to be women. And it looks like that's the case. Now, the good news is, all right, is most of you guys that are women are going to be healthy. But in a normal class size that I have, I believe in terms of total population, anywhere between 1 or 2 of you should have some kind of thyroid disorder. So it affects about 5 to 10% of the population. So it is usually going to affect women a lot more than males. And usually you want the ones, and you don't want to have a disorder, but if you have hyperthyroidism, Those are the people that can eat like a gallon of ice cream and lose weight because the metabolism is so high. Now, for us, that's great because you could eat a gallon of ice cream without having any guilt, right? Without gaining weight. But in terms of the way we have evolved through the many, many, many hundreds of thousands of years of evolution that we have for our bodies, what we're going to see is that with evolving, right, the last thing we want to do is burn more energy than we can take in. The great thing about us right now is we always know when our next meal is coming. But as we're evolving, and even in different parts of the world right now, even in different parts of America right now, there are people that can't get enough food into their bodies. And then they become inefficient, right? So then they're in calorie deficit. Well, what happens when you have some kind of thyroid disorder is that you eat a lot of calories. For most people, you will gain weight because you're storing it for some time when you're not eating. But for people that have a thyroid disorder, their metabolism so high, they just burn it off, right? They don't gain weight. And now you think that's a great problem to have until you realize your heart and your brain is also hyperactive. So as a heart becomes hyperactive, you start having arrhythmias. As your brain starts to become hyperactive, because those are cells as well that has higher metabolism now, those cells also become more active and people have a hard time sleeping. They have a hard time staying on track when they're talking. They just talk a million miles per second and they will have change in topics, all right, in the middle of a conversation because they just can't keep up, right? They just are going so fast, the brain's going so fast. So that's not good. We need to be able to find the issue. And if it's a thyroid issue, we give them an isotope of iodine. The more active the iodine, the more active the thyroid, the more iodine it picks up. So if I give you an isotope of iodine that has an extra neutron in it, what happens? It picks up that area that's hyperactive, picks up more of that radioactive isotope. And what happens then? The radioactivity, right, starts to decay. The neutron starts to be released. As it starts to be released, when I shoot an X-ray, some kind of radiation there as well, it glows. So now I know exactly where the actual area of hyperactivity is. That way, I do not remove your whole thyroid. I can only, and I should only, remove the area that glowed, and we can pinpoint the actual region that is hyperactive. Now, they do use isotopes as a way of treating thyroid disorders as well. It's a stronger type of radioactivity. It gets, again, radioactive isotope of iodine, right? The more active the tissue, the more radioactive iodine, and then it acts like a poison to kill off those hyperactive cells. The cells that are of normal activity, well, those cells, they don't pick up as much of that toxic radioactive iodine and they stay alive. They're still then protected. Whereas the ones that are hyperactive takes up more of that toxin, more of that radioactive iodine, and they die off as a cause of this. Now we'll talk about electrons and electron and chemical bonding. So we talk about chemical bondings and electrons. I kind of like discussed it before, right? All of these elements right there. So move to this part of these next two slides right here about covalent and ionic bond. And we're going to discuss it just by looking at the periodic table of elements right here. When we're looking at the periodic table of elements, what I want you to understand is, right, the most important concept here is understanding that all of these elements, all these atoms over here, they're going to do whatever they can to achieve noble gas-like status. Meaning what? Right? For fluoride right here, fluoride is at 7 valence electrons. All it has to do somehow is steal one more electron somehow. If it does somehow take an electron, it gains an electron, it has 8 electrons. Now that fluorine becomes neon gas-like. What happens then? It fills its valence shell. It undergoes it completes what they call the octet rule. The octet rule means that you have filled out your electron shells and orbitals. When you do, boom, right? Fluorine or fluoride right here will turn into a neon gas-like stability. Perfect. Oxygen. For oxygen, it needs to gain somehow 2 electrons. Now, when it gains electrons, it can either steal it or it can kind of share it. With fluorine, fluorine's so close that usually with fluorine, right, if we have hydrogen and fluorine together and we mix it together, well, with hydrogen fluoride, what happens? Well, hydrogen fluoride right here, hydrogen has 1 extra electron. Fluorine, it needs 1 extra electron. So this atom is very strong. It's going to try to take that electron from hydrogen. And when we react it together, it does. It's going to remove this electron from hydrogen. That electron is going to go right to fluorine. As you have that transfer of electron from one element or one atom to the next, now we start seeing some change in the charge right here. So hydrogen fluoride, fluorine right here will gain an electron and becomes noble gas-like. Now keep in mind, and I'm going to write it right here, when you gain an electron, fluorine should have 7. Now it's stolen hydrogens and now has 8. When you gain electrons, electrons are negative charge. So fluorine will have a negative charge after they've been mixed together. If you've ever seen some of these with negative charges, that's why. Right? Positive charge, negative charge. Right? We call that an ionic bond. So what happens? And the best example of an ionic bond is not actually fluorine, but sodium and chlorine. Now with sodium and chlorine, these are great examples of an ionic bond that forms. When we put these two, when we put these two atoms together, let's take a look what happens. Chlorine, just like fluorine, 7 valence electrons, it needs to get 8 to fulfill its octet rule. Sodium's way out here, right? Sodium has 1 extra valence electron. Now, sodium can somehow try to gain 7 electrons. Impossible. It's not going to be able to. Or it can give away its 1 extra valence electron. If it gives it away, it loses electron. From 11, now it loses an electron, it goes to 10. With 10 valence electrons, it becomes noble gas-like. Perfect, right? So what happens when we put sodium and chlorine together? What happens is this. Sodium right here has an extra electron. I'm just going to write it as a E minus right here. The valence electron that's extra, the sodium wants to give that extra electron, then goes to chlorine. When chlorine receives the electron, it goes from number 7 to number 8. It becomes noble gas-like. So it wins. Perfect. Of course it wants to react, right? It's going to win. So what happens when you transfer an electron from sodium to chlorine? What happens is this. Chlorine gains an electron. As chlorine gains an electron, electrons are positively charged, are negatively charged. As electrons that are negative goes from sodium, it's got 1 extra, goes right to chlorine. Chlorine gains that negative charge, and this negative charge shows that there's a direct transfer of the electron from sodium to chlorine. What happens then? Well, sodium lost that negative charge. When it loses a negative charge, did we remove a proton? No. All we did was remove an electron. Now, we have now at that point 11 protons, but only 10 electrons, right? Now we have a charge difference, right? So there's more protons, 11, than electrons when we put these two together, right? There's one more proton. And that's what we see here. Protons are positive charge. So when we gain that, when we lost that electron from sodium and we give it to chlorine, chlorine gained that negative charge. There's a direct transfer of a full electron. That's why you have a complete negative charge. Sodium, though, lost an electron. When you lose a negative charge, a whole negative charge, like sodium just did, you don't become nothing, right? Now you have more protons than electrons. So protons are positive charge. When you lose that one electron, you have one extra proton, and that's what we see here, right? That's why you always see sodium when it's with something else, right? Usually with chlorine. This is table salt, right? This is what we usually see sodium written as a sodium positive charge. And then if it's table salt, chlorine negative charge. Other ones, right? How many times have you guys seen calcium with a +2 charge? Even though that's not calcium, right? Calcium with a +2 charge right here. What does that mean? Well, let's talk about calcium then. Here's calcium. It's got 2 extra electrons on its valence shell. It can try to react and gain 6 more. Or with calcium, we can react it with chlorine as well. And when we react it with chlorine, chlorine wants those electrons, really wants those electrons, right? Remember, it's very close to fulfilling its octet rule. It's got 7, it needs to get an 8. But one molecule of chlorine, right, cannot receive both of those electrons. So what do we need? We need 2 chlorines then, right? Each of the chlorine will then receive a negative charge from calcium. So each of the calcium has 2 electrons. When we react it with chlorine, what happens? You can't just have one molecule of chlorine, because if you did, you just have 1 electron. You need 2 of them. So now we have 2 molecules of chlorine. Calcium will have 1 electron go to 1 molecule, and another electron goes to another molecule of chlorine, right? At that point, calcium has lost 2 electrons. When it lost 2 electrons, it still got 20 protons. Now it only has 18 electrons. When it's at 18 electrons, it's become argon gas-like. Perfect. It has fulfilled its octet rule by losing electrons. Since it lost 2, there's now 2 more protons than electrons. 20 protons, 18 electrons. This is where we get the +2. How about chlorine? Each of the chlorine gained an electron. So each of them are going to have negative charge right here. Perfect. So this is the chemical formula for calcium chloride. CaCl2. So that's it. Again, this is how we make that actual, right? How we make calcium chloride right here. And this is an ionic bond we're going to form, right? So when we have direct transfer of electrons, that's not an interaction. There's a direct transfer. But what happens is this. Now we have positive charge on sodium, negative charge on chlorine. Now we have a magnetic attraction between these two when we form sodium chloride. Same thing with calcium chloride. Calcium has +2, chlorine has -1 for each one. Well, opposites attract. The positive and the negative charges attract each other, and they form a little connection, a bond between them. This ionic bond can be pretty strong. If you look at table salt is a solid, right? It's salt. So what happens with table salt right here? What we're going to see is there's going to be an interaction between the sodium and the chlorine right here, and that forms a solid. Now, with ionic bonds, the cool thing with ionic bonds is that you can disrupt the bond. So in ionic bonds, atoms exchange electrons. By exchanging and directly transferring an electron from one atom to another, you are then going to create charges. So sodium and chlorine. Sodium lost an electron. Chlorine gained electron. Now you have charge difference between those two. Before, they were uncharged, but when you mix both of them together, you now have a charge difference because of that ionic bonding. The ionic bonding also is strong because now you have this magnetic attraction as well between the positive charged sodium and the negative charged chlorine. Now, what then we're going to form is an ion. An ion is an atom that loses or gains electrons and becomes charged. Ions can be positively charged and be called a cation. The cation here is sodium. Or you're going to have negatively charged anions. The anions are the ones that gain the electron, like sodium did, and now it has negative charge. So cations, positive charge, anions, negative charge. In an ionic bond, cations and anions are attracted to each other and become magnetically attracted to each other, keeping them close to each other. Now, the good news about ionic bonds is they're kind of strong. We see them a lot in our body, right? You don't usually see calcium as just free calcium. You always usually see it with a positive 2 charge, even in our body. And what we're going to see about cations is this. What happens if we add a little bit of water to salt? You guys have all seen a saltwater fish tank, not a freshwater one, right? Next time you go to like a pet store, if they have an area for fish tanks, go in there and look at the brightness of the fish, of the corals that are in the saltwater tank. And then go look at the freshwater and see if you can tell any difference between the water. If you look into the actual tank and you look at the clarity of the water, you should not see any salt crystals in the middle of that tank. The reason why is this. When we add water to the mix, water can disperse this. It can separate the sodium from the chlorine. And we'll talk about how in a second. All right. So when you're looking at a saltwater tank, unless you're looking at the edges, right? If you're looking right in the middle, there's a lot of water interacting with sodium chloride. As it reacts, it separates those two. Now, what should be crystals have been separated, and now they're soluble, right? Now, what happens then? Well, usually if there's a lot of water, the water stays and it maintains and keeps sodium and chlorine separated from each other. But what happens if the water evaporates? On the edges of the fish tank, where the plastic is, there's going to be a little bit of evaporation. In those areas where salt water has probably splashed a little bit, and that salt water now is no longer part of the larger tank, right? It's just by itself as a couple droplets. Well, water evaporates. As water evaporates, the sodium and the chlorine right here will be attracted to each other again. And you'll see crystals on the edges where there's a loss of water from evaporation. Right. Now, we'll talk in a second. Now, why is it that some atoms undergo ionic bonds And some atoms that we'll discuss in a second will talk about and undergo something, right, called covalent bonds right here, right? So ionic bonds doesn't occur when we react two different elements all the time. There are some atoms and elements that undergo covalent bond, whereas ionic bonding is a complete exchange of atoms. Covalent bond is a sharing of electrons. Now, some of the elements are very, very what we call electronegative, electron hungry. So let's see which ones. I'm going to go back to that one slide that shows all the different colors, the red and the white right here. All the red colors right here are going to be the elements, the atoms that are going to be most electron hungry. So if you take a look, fluorine, chlorine, bromine, iodine, these are all shades of red. Fluorine is the darkest shade of red. Now, it kind of makes sense that these have the higher values for electronegativity. Why? Because these atoms are the closest we get to the noble gases. They usually only need one electron to fulfill its octet role. So it will do whatever it can to steal the electron when we have it combined with any of the elements or atoms on this side. So if you take a look, fluorine has an electronegativity number of 4. That's very strong. When we have hydrogen react with it, hydrogen isn't even weak, it's got 2. But what happens is there's a huge difference, 2.1 and 4. Fluorine is like the older brother. It's going to try to take the electrons from fluorine. Since this older brother is so much stronger, it can and will take hydrogen's electron. Right? Electronegativity is the strength of the ability to steal electrons. Chlorine, same thing. We have hydrogen chloride or potassium chloride. Take a look at potassium. It's got an electronegative that's 0.8 value, meaning it's pretty weak. If we react it with chlorine with 3, right, there's a huge difference in electronegativity. If we react these two, they will never form a bond where they're sharing electrons. Chlorine will be so strong, it will steal the electron directly from potassium. And potassium is on the same column as sodium and lithium and hydrogen, meaning it's got 1 extra electrons. Potassium wants to give that electron away. If it does, it becomes argon gas-like. It wins. If chlorine takes the electron from potassium, it adds an electron and becomes argon gas-like as well. So what happens? It wins as well. When you have these two elements, sodium and chlorine react with each other, when you have those atoms react with each other, it's going to form an ionic bond, not a covalent bond. A covalent bond is a sharing of electrons. That's when you have electrons that are, or you have elements and atoms that have very close electronegativity scale. Let's take a look. How about carbon when it reacts with hydrogen? Right? Now, I'm just going to write some of these here. When carbon reacts with hydrogen, what happens? Look at their electronegativity. 2.1, 2.5, very close. Carbon is not going to steal any electrons from anybody. Right? Take a look at carbon, 2.5, right? You can react it with anything here, and it's going to usually form a covalent bond. Even carbon and oxygen will form a covalent bond. Now, what happens though, when carbon reacts with something with very similar electronegativity right here? Carbon is going to form a bond where they're sharing electrons. With carbon, carbon was smack dab in the middle, right? It's got, all right, if you take a look, it's going to have 4 valence electrons. And those 4 valence electrons means that it's got 4 electrons that can be shared. So when we share them all, If we have hydrogen, hydrogen can only just pick up one electron and share it. That's it. So you can't just have one hydrogen and one carbon. Instead, we have 4 electrons. We're going to need 4 hydrogens to react with it. Each of the hydrogen is then going to react with one of the electrons in carbon, and we're going to form this structure that I know all of you guys have smelled before, right? This is methane, CH4. Methane right here is found when you have 4 hydrogens reacting with carbon. Why 4 hydrogens? Because carbon has 4 valence electrons. When we have a covalent bond, each of the electrons, the 4 from carbon and the 4 more from each of the hydrogens, each of the electrons are shared for each of the atoms. So for carbon, it wants to bind with 4 hydrogens. Why? Because it's going to have its original 4 valence electrons, and now it's going to have 1 electron from hydrogen, another one from another hydrogen, another one from a third hydrogen. And what happens if carbon reacts with a 4th hydrogen? It gains another electron and it turns into neon gas-like. Perfect, right? This is a covalent bond, a sharing of electrons. And because with carbon, the sharing is almost always equal, right? Not one of these elements is going to be so much stronger that it can steal the electron and pull it towards itself, right? Usually when carbon is found as the backbone of any chemical structure, carbon always shares those electrons equally. So at any one time, when carbon and hydrogen are sharing its electrons, the electrons 50% of the time will be towards carbon. 50% of the time will be towards hydrogen. They're equally shared. Why? Because of these electronegativity numbers. Now, we call that, and this is very important right here, right? We call that equal sharing of electrons that we see here. The equal sharing of electrons, we call that a non-polar covalent bond. And right, when we talk about science, we want to be as specific as possible, right? In other words, there's a difference. If there is let's say I'm asking a question on a quiz or a test, and the question is in regards to what are the type of bonds formed by carbon? Well, usually, if you give and write down just covalent bond, that's not enough detail because there's 2 forms of covalent bonds, right? There's polar and nonpolar. So you have to go with the full name, nonpolar covalent bonds. Again, covalent bonds, sharing of electrons. Now, all of you have already heard of carbon dioxide, CO2. What is CO2? Right? That's what we exhale, obviously, right? And with carbon dioxide right here, we have 2 oxygens for every carbon. Well, take a look, right? What does that mean? I mean, carbon has 4 electrons. It's only reacting with 2 oxygens, though, right? Normally, carbon's going to react with 4 different other atoms, but there's only 2 oxygens. How does that work out? Take a look. Oxygen, right, has, when you take a look at it, has 6 valence electrons. Because oxygen has 6 valence electrons, and again, if you want, you guys can go back and forth with that. And then this periodic table, oxygen has a number 6 on its top of its column. That means that in order for it to fulfill its octet rule, it has to gain 2 electrons, either by direct stealing and taking or by some kind of sharing of electrons. What we're going to see is this. Sometimes, right, with carbon, and with some of like boron, sometimes it's definitely with nitrogen and sulfur, right? Sometimes it can form what we call double bonds. Now, what happens with these double bonds is this, right? When carbon dioxide and water react, or when carbon dioxide, right, react and is formed, what we're going to see is you're going to have one oxygen molecule on one side, and then you're going to have a carbon in the middle, and then another oxygen on the other side. And what we're going to see is when you see a straight line, but two of them, that means that there's a double bond. Instead of one electron that's being shared, now, right, carbon has two its valence electrons on this side, two on this side. Oxygen can react also with two electrons, and the oxygen's electrons are going to be on this side. So between carbon and oxygen this side, there's 4 total electrons being shared. So what happens, right? Oxygen has its 2, and now it's sharing 2 more from carbon, 1, 2. So this oxygen has fulfilled its octet rule. How about this oxygen? This oxygen has 2, right? It needs to gain 2 electrons. It's got its 2 original, right? The end of the line is going to be the actual electron, and it's going to share 2 of carbons. What happens? It's going to have a gain of 2 electrons then. Again, when we have covalent bonds, each of the shared bonds, 1 and 2, count for each of the atoms. So they count for both oxygen and carbon. So 1, 2 electrons, 3, 4 electrons is going to become neon gas-like. Perfect. How about carbon? Why does it want to react with only 2 oxygens? Well, remember, the end of each of the lines represents an electron. So here's 1 electron from carbon, 1 electron from carbon, that's 2, 3, 4, 5, 6, 7, 8. 8 electrons, that carbon becomes neon gas-like. Perfect. That's why we usually see, right, these double bonds when we see carbon and oxygen mixing together. Any questions so far? I know that's a lot of chemistry. And again, just a little kind of, because of how bad the whiteboard and the writing board is on, what do you call it? On Zoom, there is a whiteboard, but it's really hard to actually use. And sometimes, can you guys see this? I'm hoping you can. So what happens with the writing board is we can talk about, carbon. And usually when we talk about electrons, we're going to use little dot structures, right? But it's really hard to control this. That's why for some of this, especially for chapter 2, I prefer to use my original, right, in-class lectures. So here's carbon with its 4 dots, the 4 valence electrons. And now here's hydrogen, right? Each of the hydrogen has its own dots. I'll try to make oxygen a different color, or hydrogen a different color. And what we're going to see is this is methane. So here's a dot right here for an electron. Again, this is why I don't like using the whiteboard. It makes it so that I have a hard time just even writing like the letter H. Now what happens? We have CH4. Each of the hydrogen has 1 electron and a second. That's 2 electrons. Now that hydrogen is very similar to helium, the noble gas, right? Here's hydrogen here. Each of the hydrogens has its own electron and carbons. This has 2 electrons. It becomes neon gas-like. So there's this one. So there's this one. How about carbon? Carbon has 1, 2, 3, 4 electrons. That's its own. And then it's going to share 1, 2, 3, 4 electrons from the 4 hydrogens, right? it has 8 electrons now, and it has fulfilled this octet rule. Perfect. Now, how about something like this? And then we'll take a break. Water, H2O. So here's H2O. I'll make this one blue. Now, when we look at water right here, please tell me you can see it, right? When we look at water, oxygen right here has electronegativity of 3.5. Hydrogen is 2.0. Now, what we're going to see is it's very hard to steal 2 electrons from just one atom right here. So this, when we have water being formed, you aren't going to form an ionic bond between those two. You'll have to form a covalent bond. But if you look at the electronegativity, oxygen is so much stronger than hydrogen that you will not be sharing the actual electrons equally. Not like what we saw with methane, right? CH4, right? There were the electrons at any one time is shared equally between carbon and hydrogens. But the reason why that works is take a look at the electronegativity. 2.5, 2.1, very close. Hydrogen and oxygen, though, completely different, right? There's at least, or there's about 50% greater electronegativity for oxygen than hydrogen. So when these are forced to interact, H2O, there's going to be a sharing of electrons, but one of the constituent, the oxygen, is much stronger, more electronegative. And it's going to form what we call a different type. It's going to form a different type of covalent bond. So let's draw this out. Here's oxygen. Oxygen is going to have 6 total electrons on its valence shell. So here's the dots that represents electrons. 1, 2, 3, 4, 5, 6. Now it's going to react with hydrogens. Here's hydrogen on one side, and I'm drawing it not in a straight line for a reason. And here's hydrogens, electrons right here. Now, because of the high electronegativity, at any one time, the hydrogen will be trying to take this electron and move it towards itself. Trying to take the electron from hydrogen and move it towards itself. Same thing here. The electron from hydrogen should be shared equally, but because oxygen has such higher value for electronegativity, 3.5 versus 2, because it's so much stronger, there's an unequal sharing, right? And because there's unequal sharing, what happens then? The electron from hydrogen, instead of being shared 50-50, gets pulled towards oxygen. Same thing on this side. The electron from hydrogen gets pulled towards oxygen. And now we have partial charges because of this. And what we're going to see is that there's this sign right here. This is the Greek sign for delta, or partial. So oxygen is going to kind of steal the electron. And because it's kind of taking the electron, it's got a partial negative charge, right? Let me just undo that. That looked really terrible. It's got a partial, the delta, negative charge. How about each of the hydrogens? Each of the hydrogens is having its electron stolen. If you got an electron completely stolen, you lose an electron, you become a positive charge. Here, it's still kind of sharing, so there's no direct stealing like we see in an ionic bond, or taking, right? Instead, there's a sharing, but it's like sharing, sharing something with your older brother or sister, right? I always use the example of video games. When I was growing up, video games were expensive, still is, right? So when we're growing up, if my brother and I wanted to say, get a game for Christmas, right? We'd get one game and we'd have to share it. We get Madden's, then we'd have to share Madden's football game, right, between the two of us. Since my brother is like 2 years older than me, what are the chances he's going to equally share that game? Probably not good, right? Better yet, what's the chance that he's going to actually take it and steal it from me so then I don't play it at all? A little bit higher, but I'll probably squeal to mom and then he'll get in trouble. So he doesn't want to just directly take it, but he wants to play it more with his friends. So at first, he's just going to take it and play it and play it and hog that game and not let me play it. That's what's happening here. Oxygen is a big brother. It's able to hog the electrons towards itself. Hydrogen is a little brother, right? It can only do so much to keep that game a little bit so then he can play it. It can only do so much to keep its electron, right? It doesn't want to get it completely stolen. So what happens is that instead of completely giving up and giving the electron towards oxygen and giving it a full charge, right? It only, grudgingly shares it, but shares it in an unequal fashion. And what happens, because it's shared in an unequal fashion, this oxygen gains a partial negative charge. Then, right, because the hydrogen has kind of lost its own electron, it also has a partial charge, but it's a partial positive charge on each one. Now, do you guys see what happens when I have right? This is called a, whoops, this should be positive charge. This is called a polar covalent bond. And these bonds are very different than a non-polar covalent bond. Now, at its base, what we saw with carbon and hydrogen and methane, there's equal sharing. There's still sharing with water, but there's an unequal sharing. Because there's an unequal sharing of electrons, you see these negative and positive charges everywhere. And what happens then? Well, this is just one molecule of water, right? In a droplet, the smallest droplet in the world, you're going to have billions and billions and billions of these H2O molecules. So you have a molecule of H2O right here, and then another molecule of H2O with its partial charges. All right, now I'm going to draw the lines. And now what happens, right? All those partial charges are going to be attracted to each other. So the partial charge right here, this guy right here, the hydrogens has a partial positive. This hydrogen has a partial positive. This oxygen has a partial negative. What happens? Well, this is going to start to, these molecules are going to start to interact with each other. Right? As they interact with each other, these are forces between different molecules. Right? They're not the forces that allows us to form a bond. These are forces that are intermolecular, not intramolecular. The intramolecular forces are the covalent bonds here. They help form the molecule, right? And what happens? You have all these hydrogens and oxygens start to interact with each other because this is a polar bond. And this is polar negative. So all the oxygens right here starts to interact with all the oxygens from one molecule starts to interact with the hydrogens from another molecule. And what we get now are the presence of hydrogen bonds. The hydrogen bonds, each one is very weak, right? These interactions right here, they're pretty weak interactions, right? They're definitely not as strong as an ionic bond. They're definitely not as strong as a covalent bond. But what makes them strong is the number of them, right? You have billions of H2O molecules in one droplet, and you're going to have billions of these hydrogen bonds reacting with each other from intermolecular forces, right? Because you have billions of these forces, they now start becoming strong just based on sheer numbers. And it's all due to the fact that in a polar bond, you have an unequal sharing. So then one of the atoms gains a negative and the other one gains a partial positive charge. And then all it is at this point is just opposites attracting to each other, right? This is what makes and why I want you to know the difference between a nonpolar and then this one, a polar covalent bond. All right. And you have to be very specific. When I ask you which kind of bond do we form, right? You need to say whether it's covalent or ionic, and whether if it's covalent, it's polar or nonpolar. Now, any questions? Not yet. All right, let's take a little break, 5-minute break. We come back, we'll finish up the last 20 minutes.